Right now, the nearest star beyond our Sun sits 4.24 light-years away. That sounds close by cosmic standards. It is not. If you loaded a spacecraft with the most powerful chemical fuel ever invented and aimed it at Alpha Centauri, the journey would take over 70,000 years. The obvious solution is to go faster. Much faster. 10% the speed of light would get you there in about 43 years. But here is what nobody tells you. Reaching that speed with a real spacecraft would require more energy than your entire civilization produces in a month. And that is just the beginning. The faster you push, the worse the numbers get, until physics itself builds a wall no technology can break through. If you want to understand why the stars might stay forever out of reach, tap that like button and subscribe. Now, settle in and get comfortable. Let's begin. Humans have stared at the stars for as long as we have existed. Every civilization that looked up at the night sky imagined crossing the void between those distant points of light. The ancient Greeks debated whether stars were other suns. Giordano Bruno proposed in the 16th century that each star hosted its own system of worlds. When telescopes confirmed that the stars were indeed distant suns scattered across immense distances, the dream did not die, it sharpened. If those lights were other suns, perhaps other Earths orbited them. Perhaps life, even intelligence, existed on those worlds. The question shifted from whether the stars held worlds to whether we could ever reach them. For most of human history, the question was purely philosophical. We lack the technology to leave our own planet, let alone cross interstellar distances. But the 20th century changed that. We split the atom. We built rockets powerful enough to escape Earth's gravity. We sent spacecraft to every planet in our solar system. We landed humans on the moon. Each achievement made the next seem inevitable. If we could reach the moon in a decade of effort, surely interstellar travel was just a matter of time, money, and engineering. That confidence was misplaced. Not because our engineering was lacking, but because we fundamentally underestimated what the universe demands from anything trying to cross the distance between stars. The gap between planetary travel and interstellar travel is not a matter of degree, it is a matter of kind. Moving between planets is hard. Moving between stars is a confrontation with the deepest laws of physics. To understand why, we must first understand the distances involved, and what those distances force upon any spacecraft attempting to cross them. Start with the nearest target. Alpha Centauri is a triple star system sitting 4.24 light-years from Earth. The system contains a Sun-like star Alpha Centauri A and a slightly smaller, cooler companion called Alpha Centauri B, orbiting each other in a close binary, plus a small, faint red dwarf called Proxima Centauri. Proxima is the closest individual star to our Sun, slightly nearer than its two larger companions. In 2016, astronomers confirmed that Proxima Centauri hosts at least one planet, Proxima Centauri b, orbiting within the star's habitable zone, the narrow region around a star where liquid water could exist on a rocky planet's surface. The discovery electrified the scientific community. The nearest star has a planet where conditions might permit liquid water. If there was ever a reason to attempt interstellar travel, this is it. In cosmic terms, Alpha Centauri is practically next door. If our galaxy were the size of the continental United States, the distance to Alpha Centauri would be roughly the width of a single dining table. It is the closest star system to our own, by a significant margin. The next nearest options are farther still. Barnard's star lies roughly 6 light-years away. Wolf, 359, sits almost 8 light-years out. Sirius, the brightest star in our sky, is approximately 8.6 light-years distant. Ross 128 is about 11 light-years away. If we cannot reach Alpha Centauri, we cannot reach anything. 4 light-years sounds manageable until you convert it into a distance your intuition can actually process. 1 light-year equals approximately 5.88 trillion miles. That is the distance light travels in 1 year. moving at approximately 186,000 miles per second, or about 300,000 kilometers per second. Multiply 5.8 trillion by 4.24, and you get roughly 25 trillion miles. Written out fully, that number has 14 digits. It is a distance so vast that no human sense can hold it, no analogy can fully capture it, and no amount of staring at the number makes it feel real. Try an analogy anyway. If the sun were the size of a grain of sand placed on a table in front of you, Earth would be a microscopic speck, orbiting about 1 inch away. The nearest star, Alpha Centauri, would be another grain of sand sitting roughly 4.5 miles from your table. Everything between those two grains, 4.5 miles of open space, would contain essentially nothing. Just vacuum, interstellar dust, and the occasional stray particle drifting through the void. That is the neighborhood in which we are trying to travel. The nearest destination sits 4.5 miles of emptiness away from a grain of sand, and we are smaller than the speck orbiting that grain. Now try another comparison. If you could somehow drive a car at highway speed, say 100 kilometers per hour toward Alpha Centauri without stopping, the journey would take approximately 46 million years. The dinosaurs went extinct 66 million years ago. You would not have finished the drive yet. In fact, you would still be roughly 20 million years away. But we do not need to think in terms of cars. We have spacecraft. The fastest spacecraft humanity has ever built provide a more relevant benchmark. Consider Voyager 1, launched in 1977. After gravity assists from Jupiter and Saturn, Voyager 1 now travels at about 17 kilometers per second relative to the Sun. That is roughly 38,000 miles per hour over 61,000 kilometers per hour. Voyager 1 is the fastest human-made object that has left the solar system and entered interstellar space. At Voyager's speed, crossing the distance to Alpha Centauri would require approximately 75,000 years. 75,000 years. To feel the weight of that number, consider that when Voyager 1 was launched, humans had only been practicing agriculture for about 12,000 years. All of recorded human history, every empire that rose and fell, every war fought, every book written, every language spoken, every religion founded, every discovery made fits within roughly 5,000 years. Multiply that entire span of civilization by 15, and you begin to approach the travel time. Or think of it this way. If a crew had departed on a Voyager-class spacecraft when Homo sapiens first appeared in Africa roughly 300,000 years ago, they would have completed the journey roughly 4 times over. Yet no single generation aboard would have seen the destination grow closer in any meaningful way during their lifetime. This is the first uncomfortable realization. Our current technology is not merely slow for interstellar travel, it is irrelevant. Voyager-class speeds do not reduce interstellar distances to something achievable. They merely reveal how absurdly far the stars actually are compared to anything we have accomplished in space. Voyager 1 has been travelling for nearly 50 years and has covered roughly 1 light day of distance, about 26 billion kilometres. It would need to travel for 75,000 years to cover 4.24 light years. The ratio between what we have done and what we need to do is roughly 1 to 1,600. If walking to the corner store represents what Voyager has achieved, reaching Alpha Centauri represents walking from London to Baghdad. The New Horizons spacecraft, which flew past Pluto in 2015, travels at roughly 14 kilometers per second, even slower than Voyager. The Parker Solar Probe, during its closest approaches to the Sun, reaches speeds of about 192 kilometers per second, the fastest any human object has ever travelled. But the Parker Solar Probe achieves this speed only during brief perihelion passes, and it cannot sustain it. Even at its peak velocity, reaching Alpha Centauri would take over 6,600 years. The Juno spacecraft, currently orbiting Jupiter, reached about 74 kilometers per second relative to Jupiter during its arrival maneuver, still hopelessly slow for interstellar distances. Every spacecraft humanity has ever built, from Sputnik to the James Webb Space Telescope, operates at velocities that render interstellar travel meaningless. The distances are simply too vast for our current capabilities. Let us put these spacecraft velocities in one more context before moving on, because the contrast between what we have achieved and what interstellar travel demands is itself the beginning of the energy story. Humanity's greatest triumph in space travel is arguably the Apollo program. In December of 1968, Apollo 8 carried 3 astronauts around the Moon and back a round-trip distance of roughly 770,000 kilometers. The journey took about 6 days. It was, at the time, the farthest any human being had ever traveled from Earth. It remains among the farthest to this day. The distance to Alpha Centauri is approximately 40 trillion kilometers. That is roughly 52 million times the distance to the Moon. If we could repeat the Apollo 8 mission 52 million times each time, pushing the endpoint a little farther out, we would eventually reach the nearest star. The entire Apollo program, from conception to completion, took about 11 years and cost roughly $200 billion in today's currency. Multiply that by 52 million, and you get a cost measured in quadrillions of dollars and a timeline measured in hundreds of millions of years. This is obviously absurd, but the absurdity is precisely the point. The gap between planetary and interstellar travel is not a gap that incremental improvement can bridge. It is a chasm of a fundamentally different character. Within our solar system, distances are measured in light minutes or light hours. The Moon is 1.3 light seconds away. The Sun is about 8 light minutes away. Mars at its closest is roughly 3 light minutes from Earth. Jupiter is about 43 light minutes. Even Pluto, at the outer edge of the major planets, is only about 5.5 light hours from the Sun. Voyager 1, nearly 50 years into its journey, is about 22 light hours from Earth. Alpha Centauri is 4.24 light years away. The jump from light hours to light years is a jump of roughly 4,000 times in distance. It is the difference between a sprint and a marathon, except the marathon is 4,000 times longer than the sprint. And the sprint already took decades of effort and the combined resources of the most powerful nation on Earth. This scale difference explains why the transition from solar system exploration to interstellar travel is not a smooth extension of existing capabilities. It is a phase transition, like the difference between heating water and boiling it. Below the transition, incremental improvements yield incremental results. Above the transition, the rules change entirely. New physics dominates, new constraints emerge, and the most important of those new constraints is energy. The intuitive response to these numbers is obvious. Go faster. If 17 kilometers per second is too slow, find a way to travel at 100 or 1,000 or 10,000 kilometers per second. Reduce that 75,000-year journey to something a human crew could survive. This is where most people's thinking about interstellar travel begins and often ends. They see the problem as one of speed. Build a better engine, burn a hotter fuel, push harder. The stars will come within reach once we find the right propulsion technology. This intuition is not wrong in principle. Speed absolutely does reduce travel time. The question is how fast you need to go and what that speed actually costs in terms of energy. It is here in the relationship between speed and energy cost that the dream of interstellar travel collides with the hard physics of reality. Let us work through the arithmetic deliberately. Suppose you want to reach Alpha Centauri within a single human lifetime, say 50 years door to door, including time for acceleration, cruising, and deceleration. That requires a cruising speed of roughly 8.5%, the speed of light, assuming you spend most of the journey at cruise velocity. Round it to 10% for simplicity and for a margin that accounts for acceleration and deceleration phases. 10% of light speed is about 30,000 kilometers per second. That is nearly 2,000 times faster than Voyager 1. At that velocity, you would cross the distance from the Earth to the Moon in about 13 seconds. You would pass Mars at its closest approach to Earth in roughly half an hour, You would cross the entire diameter of Earth's orbit around the Sun, about 300 million kilometers in under 3 hours. The solar system would shrink to a brief departure corridor measured in hours rather than the years it takes current spacecraft to traverse it. 10% of light speed would place Alpha Centauri roughly 43 years away. Still, a long mission, a crew that departs at age 30 arrives at age 73, assuming no relativistic time dilation but conceivably within a human lifespan, especially if life extension medicine improves over coming centuries. Faster speeds shorten the timeline further. At 20% light speed, the journey takes about 21 years. At 50%, roughly 8.5 years. At 90%, a little under 5 years. At speeds above 90% light speed, relativistic time dilation further shortens the experienced travel time for the crew, even as external observers measure longer durations. These travel times seem encouraging. Surely a sufficiently advanced civilization, perhaps a few centuries more advanced than ours, could manage 10 or 20% of light speed. The distances are large, but they shrink rapidly with velocity. The problem, it would appear, is purely technological. We just need better engines and more energy. Time will take care of the rest. This optimism is deeply embedded in the culture of space exploration. Science fiction has taught generations of viewers and readers that faster propulsion is always around the corner. Warp drives, hyperspace jumps, fusion engines, and ion drives populate fictional universes where the only barrier between civilizations and the stars is the next engineering breakthrough. The narrative arc is always the same: identify the problem, fund the research, invent the solution, and cross the void. Human ingenuity conquers distance. The history of actual space exploration seems to support this narrative. In 1903, the Wright brothers flew a powered aircraft 120 feet at under 11 kilometers per hour. 66 years later, Apollo 11 carried astronauts to the moon at roughly 40,000 kilometers per hour, a speed increase of nearly 4,000 times. If similar progress continued, if human travel speed increased by another factor of 4,000 over the next 66 years, we would reach a significant fraction of the speed of light by the early 21st century. Of course, that has not happened. Human spacecraft have increased in speed only modestly since the Apollo era. The exponential progress in travel speed that characterized the first century of powered flight has stalled. But even if it had not stalled, even if we somehow achieved the same rate of exponential speed improvement that characterized the transition from propeller aircraft to rockets, we would still face a barrier that no previous transportation revolution encountered. The barrier is not in the engineering, it is in the physics of energy and motion. The critical difference is that every previous speed challenge in human history had a finish line, a specific velocity or energy level beyond which the problem was solved. Interstellar travel has no such finish line. Every increment of speed reduces travel time, while simultaneously increasing energy cost on a curve that steepens without limit. You are never through the barrier. You are always climbing it, and the higher you go, the steeper the slope beneath your feet. But this hides an assumption that most people never examine. It assumes that increasing speed is merely an engineering challenge, that with enough ingenuity and resources, the velocity problem can be solved the way we solved previous transportation barriers. The reality is fundamentally different. Speed is not free. Every increment of velocity costs energy, and the universe does not charge a flat rate. It charges on a curve that starts steep and becomes catastrophically steep as you approach the speed of light. Think about it this way. When you drive a car from 0 to 60 miles per hour, you burn a specific amount of fuel. If you then accelerate from 60 to 120 miles per hour, you do not merely burn the same amount of fuel again, you burn roughly 4 times as much. The energy required to move an object scales with the square of its velocity. This is not a technological limitation that better engineering can overcome. It is a law of physics. Kinetic energy, the energy an object possesses by virtue of its motion, equals 1/2 times the mass, times the velocity squared. That squared term means energy does not rise politely and proportionally with speed. It climbs aggressively. Double the speed, quadruple the energy. Triple the speed, 9 times the energy. 10 times the speed, 100 times the energy. 100 times the speed, 10,000 times the energy. The relationship is not linear. It is not even gently curved. It is a parabola opening upward, and at interstellar velocities it becomes a wall. For everyday speeds, cars on highways, aircraft at cruising altitude, even spacecraft in orbit, this quadratic scaling is a manageable nuisance. The velocities are small enough that the squared term adds cost without creating a barrier. A jet aircraft at 900 km per hour uses roughly 4 times the fuel per kilometre as a propeller plane at 450 km per hour. Expensive, but not impossible. But interstellar travel demands velocities millions of times greater than anything we encounter on Earth. At those speeds, the squared relationship stops being a nuisance and becomes a wall that grows taller with every additional kilometre per second. The energy does not trickle upward, it erupts. At 10% of light speed, the kinetic energy of a modest 100,000 kilogram spacecraft already approaches the monthly energy output of all human civilization. At 50% of light speed, it exceeds annual global production. At 90%, it enters a realm where relativistic physics warps the calculation further, bending the energy curve upward toward infinity. And all of this describes only the energy of motion itself, the bare minimum energy that must be embedded in the spacecraft's velocity regardless of how that velocity is achieved. It says nothing about the energy needed to produce the fuel, nothing about inefficiencies in the propulsion system, nothing about the energy lost as waste heat. It is the thermodynamic floor, not the engineering ceiling. Every historical leap in human transportation overcame an energy barrier. Crossing oceans required sails that could harness wind energy for months on end. Crossing continents by rail required burning coal at industrial scales. Crossing the sound barrier required jet engines that consumed fuel at rates unimaginable to propeller-era engineers. Reaching orbit demanded chemical rockets of staggering power and wastefulness. In each case, the barrier seemed insurmountable until the right technology arrived, and the breakthrough opened a new regime of travel the previous generation could barely imagine. But interstellar travel is different in a way that matters profoundly. The energy barrier is not a threshold you cross once and leave behind. The sound barrier was a threshold. Once you had enough thrust, you punched through and supersonic flight became routine. Orbital velocity was a threshold. Reach 7.8 kilometers per second and you are in orbit. Interstellar speeds present no such threshold. Instead, the barrier is a continuously steepening curve. There is no single breakthrough speed where the problem suddenly becomes manageable. The problem becomes progressively more severe the faster you try to go, with the curve bending ever more sharply upward, offering no plateau, no relief, and no mercy. This is the seed of the energy wall, not a single dramatic barrier, but a compounding escalation that turns every improvement in speed into an exponentially more expensive proposition. The stars are not merely far away. The universe charges a brutal price for any attempt to cross the gap quickly. And we have not even begun to examine how bad the numbers truly get when you account for fuel mass ratios, relativistic corrections, and the need to decelerate at the destination. Consider what this means for the dream that opened this story. Every child who has looked at the night sky and imagined visiting those distant points of light, every science fiction story that depicted sleek starships jumping between star systems, every serious proposal for interstellar colonization, all of them implicitly assume that speed is a solvable problem, that the gap between our current capabilities and interstellar velocities is a technological gap, like the gap between horse-drawn carriages and automobiles, a gap that progress will close. The energy wall says otherwise. It says that the gap is not technological in nature. It is physical. It is not waiting to be solved. It is a permanent feature of the landscape, as fixed and unalterable as the speed of light itself. The wall exists not because our engines are too weak, but because the universe charges too much for speed. And the charge is not an arbitrary toll that a sufficiently advanced civilization can negotiate or circumvent. It is embedded in the fundamental equations that govern how energy relates to motion equations that apply equally to a chemical rocket and to a hypothetical starship built by a civilization 1,000,000 years ahead of us. The dream is not dead, but the dream must contend with a universe that was not designed for easy interstellar travel. The distances are merely the most visible problem. Behind the distances, hidden in the mathematics of kinetic energy and the rocket equation, lurks a far more formidable obstacle, an energy cost that rises without limit as you push toward the speeds that would make interstellar distances manageable. What comes next reveals exactly how that price is calculated and why the bill arrives in numbers that would strain the resources of an entire civilization. The physics of motion assigns a specific energy cost to every kilogram traveling at every speed. This cost is not negotiable. It does not depend on the engine, the fuel, or the ingenuity of the engineers who build the spacecraft. It depends on only two quantities: how much mass is moving and how fast it is traveling. Kinetic energy equals 1/2 times mass times velocity squared. This equation is taught in introductory physics courses around the world. It appears simple. For interstellar travel, it is devastating. The squared velocity term creates a relationship that punishes ambition. Moving a spacecraft twice as fast does not cost twice the energy. It costs 4 times the energy. 3 times the speed demands 9 times the energy. 10 times the speed demands 100 times the energy. This scaling is relentless, and it applies before any engineering considerations enter the picture. It is not a problem to be solved. It is a property of the universe, as fundamental as the charge of an electron or the constant speed of light. Let us ground this with concrete numbers, beginning small and scaling upward. Take a reference spacecraft, massing 100,000 kilograms, roughly the mass of a Boeing 737 airliner. This is deliberately modest. A crude interstellar vessel with life support systems, radiation shielding against cosmic rays and interstellar hydrogen impacts, food production or storage for decades, scientific instruments, medical facilities, communication systems, spare parts, structural mass, and engines would likely mass several million kilograms. The International Space Station, which supports a crew of 6 in low Earth orbit with regular resupply, masses about 420,000 kilograms. An interstellar vessel must be entirely self-sufficient for the entire journey. Estimates for crewed interstellar vessels range from 1 million to 100 million kilograms depending on crew size and mission duration. We will use 100,000 kilograms to show how severe the energy requirements become even at minimal scale. At 1% the speed of light, 3,000 kilometers per second, the classical kinetic energy of this spacecraft is approximately 4.5 times 10 to the 17th joules. To translate this into something tangible, a large modern nuclear power plant generates about 1 gigawatt of electrical power, which over 1 year amounts to approximately 3.1, 5 times 10 to the 16th joules. The energy needed to push our modest spacecraft to 1% of light speed equals roughly 14 years of continuous output from a large nuclear reactor. Alternatively, it represents the energy released by approximately 107 megatons of TNT, over twice the energy of the largest nuclear weapon ever detonated, the Soviet Tsar bomber. 1% of light speed is 3,000 kilometers per second. That is impressive by any human standard, about 176 times Voyager's speed. But the travel time to Alpha Centauri at this velocity is approximately 424 years. Better than Voyager's 75,000 years by a factor of nearly 200, but still entirely useless for a crewed mission. No crew survives 424 years. Even a generation ship, a vessel designed to sustain multiple human generations during the journey, faces enormous challenges over 4 centuries of isolation. Pushed to 5% light speed, 15,000 kilometers per second. the kinetic energy scales by a factor of 25, because velocity increased by a factor of 5, and the square of 5 is 25. The kinetic energy is now approximately 1.13 times 10 to the 19th joules. Let us compare this to something concrete. Global human civilization currently consumes energy at a rate of roughly 18 terawatts, 18 trillion watts, which over 1 year amounts to approximately 5.7 times 10 to the 20th joules. The energy to accelerate one spacecraft to 5% light speed equals roughly 2% of all energy produced by all nations on Earth in an entire year. 2% of global annual production sounds modest as a fraction, but consider what it means in absolute terms. It represents the combined annual energy output of approximately 360 large nuclear reactors, or the total electrical generation capacity of a major industrialized nation like France, running flat out for a year, dedicated entirely to a single spacecraft that still needs 85 years to reach Alpha Centauri. At 10% light speed, the energy reaches approximately 4.5 times 10 to the 19th joules, about 8% of global annual energy consumption. We have arrived at the minimum speed that makes interstellar travel conceivable within a human lifetime, and the energy price is already extraordinary. At 20% light speed, the energy quadruples again to roughly 1.8 times 10 to the 20th joules. This now exceeds 30% of global annual energy production, almost 4 months of everything civilization generates. At 50% light speed, the classical kinetic energy reaches approximately 1.13 times 10 to the 21st joules, nearly double the entire annual energy output of human civilization. 2 full years of every watt generated by every energy source on Earth, channeled into accelerating a single spacecraft that masses less than a large commercial airliner. Pause and notice the pattern. Each increment of speed becomes dramatically more expensive than the last. From 1% to 10% light speed, a factor of 10 in velocity, the energy increased by a factor of 100. From 10% to 50%, a factor of 5 in velocity, the energy increased by another factor of 25. The curve steepens relentlessly. There is no economy of scale. There is no efficiency gain. The physics charges more for each additional unit of speed, and the rate of surcharge increases with velocity. Let us translate one of these numbers into tangible terms to feel its weight. The energy required to accelerate our modest spacecraft to 10% light speed, roughly 4.5 times 10 to the 19th joules, equals the energy released by approximately 10,700 megatons of TNT, the largest nuclear weapon ever detonated. The Soviet Tsar bomber, tested in 1961, released roughly 50 megatons. Our spacecraft needs the equivalent energy of over 200 Tsar bombers, perfectly harnessed and converted into directed thrust with zero waste. Or, consider the number in terms of electrical power. If you could connect every power plant on Earth, every nuclear reactor, every coal station, every natural gas turbine, every hydroelectric dam, every solar farm, every wind turbine into a single cable, feeding our spacecraft's engine, running them all simultaneously at maximum capacity, you would need to sustain that connection for roughly 1 month to deliver the required energy. 1 month of total global output produced by every nation on Earth, devoted entirely to a single vehicle that still needs 43 years to reach the nearest star. Now, imagine scaling to a realistic crewed vessel. A genuine interstellar ship designed to support a crew of perhaps 50 to 100 people for a multi-decade journey with closed-loop life support, radiation shielding, food production, medical facilities, maintenance workshops, communication systems, and propulsion hardware would likely mass at least 10 million kilograms. That is roughly 24 times the mass of the International Space Station. At this more realistic mass, the energy for 10% light speed acceleration rises to 4.5 times 10 to the 21st joules. This is approximately 8 years of total global energy production. 8 full years of every watt generated by every energy source operated by every nation on the planet, directed into accelerating a single spacecraft, one way. No braking at the destination. The mass of the spacecraft matters enormously, and this cannot be overstated. Every kilogram added to the payload contributes directly to the energy requirement through the kinetic energy formula. But worse, every kilogram compounds through the rocket equation. Mass is not an engineering detail to be optimized after the main design is settled. Mass is the central variable that determines whether an interstellar mission is merely wildly ambitious or flatly impossible. Every radiation shield, every life support module, every ton of food and water, every spare part and scientific instrument and medical supply adds mass that must be accelerated to interstellar velocity. And under the rocket equation, that mass does not increase the fuel requirement linearly. It multiplies it exponentially. A useful way to visualize this: imagine you are packing for a hiking trip, except every kilogram you put in your backpack forces you to carry 3 additional kilograms of food to sustain yourself under the extra weight. And that food weighs something too, requiring still more food to carry the food. A 1 kilogram tent does not add 1 kilogram to your pack. It adds 1 kilogram plus 3 kilograms of food plus 1 kilogram of food for the food. The numbers pyramid upward. Now imagine this compounding effect amplified by a factor of 20 or 400, depending on mission parameters. That is the rocket equation applied to interstellar travel. Every gram of useful payload drags an exponentially growing tail of fuel behind it. And these calculations use classical physics alone. They do not include relativistic corrections, which make the numbers significantly worse at high fractions of light speed. We will get to that shortly. For now, the classical numbers alone are staggering enough to establish the central point. The energy required to move even a small spacecraft to useful interstellar speeds rivals or exceeds the total energy output of human civilization. But energy alone does not capture the full severity of the problem. The deeper crisis emerges when you ask a practical question. How does the energy get to the spacecraft? A spacecraft is not like a car driving on a highway with gas stations every 50 miles. A car pushes against the road. The road provides the reaction force that lets the engine's power translate into forward motion. The fuel only needs to generate forward thrust. When the tank runs dry, you stop and refuel. A spacecraft in the vacuum of space has nothing to push against. No road, no air, no medium of any kind. It must carry its own reaction mass, its own fuel, and expel it backward at high velocity to generate forward thrust. This is Newton's third law in its purest form. For every action, there must be an equal and opposite reaction. To push yourself forward in a vacuum, you must throw something backward. Every chemical rocket, every ion drive, every nuclear engine ever conceived operates on this principle. The consequence of carrying your own fuel was formalized in 1903 by the Russian physicist and mathematician Konstantin Tsiolkovsky. His rocket equation, sometimes called the Tsiolkovsky equation, describes the relationship between 3 quantities: the desired velocity change of the spacecraft, the exhaust velocity of the propulsion system, and the ratio of the spacecraft's initial mass to its final mass after all fuel has been expended. The equation reads: the change in velocity equals the exhaust velocity multiplied by the natural logarithm of the initial mass divided by the final mass. The natural logarithm function makes the equation appear mild. It is anything but. When the desired velocity change is much larger than the exhaust velocity, the mass ratio initial mass divided by final mass must grow exponentially. This means the amount of fuel needed does not increase proportionally with your desired speed. It increases as an exponential function of the ratio between desired speed and exhaust speed. This exponential relationship is the single most important mathematical fact about spacecraft propulsion. It is sometimes called the tyranny of the rocket equation, and for interstellar travel, the tyranny is absolute. To understand why the exponential matters, consider a concrete comparison between orbital spaceflight and interstellar travel. Reaching low Earth orbit requires a velocity change of roughly 9.5 kilometers per second. With chemical rockets producing exhaust at 4.5 kilometers per second, the mass ratio is e to the power of about 2.1, approximately 8. This means a rocket bound for orbit is about 87% propellant by mass, with roughly 13% left over for structure and payload. This is a challenging but well-understood engineering problem. We have been building orbital rockets for over 60 years. Now consider what happens as the required velocity change grows. For a mission to the Moon and back, a velocity change of perhaps 15 kilometers per second, including orbital maneuvers, the mass ratio with chemical rockets rises to e to the power of 3.3, approximately 27. The rocket must be roughly 96% propellant. This is why the Saturn V was such an enormous vehicle. It needed to carry staggering quantities of fuel for a relatively modest mission in cosmic terms. For a probe sent to escape the solar system, velocity change of roughly 30 kilometers per second, including gravity, assists the mass ratio approaches e to the power of 6.7, approximately 800. These numbers are already pushing the limits of what chemical rockets can achieve, which is why deep space probes rely heavily on gravitational assists to gain velocity without expending fuel. And these are all velocities measured in tens of kilometers per second. Interstellar travel demands velocities measured in tens of thousands of kilometers per second. The jump from 30 to 30,000 kilometers per second, a factor of 1,000, sends the rocket equation's exponent from 6.7 to 6,700. The mass ratio leaps from 800 to a number with nearly 3,000 digits. The exponential function has no mercy. Small increases in the exponent produce enormous increases in the mass ratio, and large increases in the exponent produce increases that leave physical reality behind entirely. Let us apply the equation to chemical rockets first, since these are the propulsion systems we actually have. The best chemical propellant combinations, liquid hydrogen and liquid oxygen, produce exhaust velocities of about 4.5 kilometers per second. This is the same propellant used by the Space Shuttle main engines and by the upper stages of many modern launch vehicles. To reach 10% light speed, 30,000 kilometers per second using chemical rockets, the required mass ratio is the mathematical constant E raised to the power of 30 million divided by 4,500. That exponent equals approximately 6,667, and E raised to the power of 6,667 is a number with roughly 2,900 digits. To grasp how absurd this is, the estimated number of atoms in the entire observable universe is approximately 10 to the 80th power, a number with 80 digits. The mass ratio required for chemical rockets to reach 10% light speed exceeds the number of atoms in the observable universe by a factor with over 2,800 digits. If every atom in the universe were converted to rocket fuel, it would not come close. Chemical rockets cannot reach interstellar speeds. This is not a close call. It is not a matter of building bigger tanks or more efficient combustion chambers or lighter structural materials. The mathematics forbids it with a finality that admits no appeal. Chemical propulsion is as irrelevant to interstellar travel as a canoe is to crossing between galaxies. Nuclear thermal rockets improve the exhaust velocity to roughly 8 or 9 kilometers per second. The mass ratio for 10% light speed drops accordingly, but remains a number with well over 1,000 digits, still beyond any physical meaning whatsoever. Nuclear pulse propulsion, the concept behind Project Orion, proposed in the late 1950s, which envisioned detonating nuclear bombs behind a massive pusher plate to generate thrust, achieves effective exhaust velocities of perhaps 30 to 100 kilometers per second, depending on the design variant. These are impressive improvements over chemical or nuclear thermal systems. At 100 kilometers per second of exhaust velocity, reaching 10% light speed requires a mass ratio of e to the power of 300. This is a number with roughly 130 digits. Smaller than before, but still incomprehensibly beyond engineering reality. You cannot build a spacecraft with a mass ratio measured in digits rather than in factors of 10. Only when exhaust velocities reach truly extreme levels, thousands of kilometers per second, does the rocket equation begin to yield mass ratios that are large but physically conceivable. This is where fusion propulsion enters the analysis. But before we examine fusion, pause and consider what the progression from chemical to nuclear pulse reveals about the nature of the problem. We move from exhaust velocities of 4.5 kilometers per second to 100 kilometers per second, an improvement of over 20 times. This required moving from the chemistry of molecular bonds to the physics of nuclear explosions, from combustion chambers to detonating atomic bombs. The leap in technology is enormous. It represents moving from the chemical era to the nuclear era of propulsion. And what did this 20-fold improvement in exhaust velocity buy us? The mass ratio exponent dropped from 6,667 to 300. That is a reduction of about 95% in the exponent. Impressive, but e to the power of 300 is still a number with 130 digits. Still utterly impossible. To bring the mass ratio down to something physically meaningful, say, a mass ratio below 1000, the exponent must be less than roughly 7. That requires an exhaust velocity of at least 4,300 kilometers per second. This is 43 times faster than the nuclear pulse exhaust, and nearly 1,000 times faster than chemical rockets. The message is stark. Incremental improvements in propulsion technology do not incrementally reduce the interstellar fuel problem. Because the rocket equation is exponential, you need revolutionary leaps in exhaust velocity factors of thousands, not factors of 2 or 3 to make meaningful progress. And each revolutionary leap represents a fundamentally new physics of propulsion. Chemical to nuclear is one revolution, nuclear to fusion is another. Beyond fusion lies only antimatter, which operates at the theoretical limit of energy extraction from matter. The ladder of propulsion has very few rungs, and the top rung is already in sight. A hypothetical fusion engine burning deuterium and helium-3 could theoretically achieve exhaust velocities on the order of 10,000 kilometers per second, roughly 3.3% the speed of light. This represents a factor of over 2,000 improvement over chemical propulsion, and a factor of 100 over nuclear pulse. It is the difference between a birthday candle and a star. With fusion exhaust velocity of 10,000 kilometers per second, the mass ratio for 10% light speed 30,000 kilometers per second of velocity change is e to the power of 3. That equals approximately 20. A mass ratio of 20 means that for every kilogram of payload that reaches cruising speed, you need about 19 kilograms of fusion fuel. For a 100,000 kilogram spacecraft, the fuel mass is roughly 1.9 million kilograms, 1,900 metric tons. This number is large but not absurd. It could in principle be assembled in space. 1,900 metric tons is roughly equivalent to 4 or 5 international space stations worth of mass. Fantastically expensive by current standards, but not mathematically impossible. For the first time in our analysis, the numbers enter a regime where the physics permits interstellar speeds barely, grudgingly, and only for acceleration. But this window comes with caveats so severe they threaten to slam it shut. First, the calculation covers acceleration only. The spacecraft arrives at Alpha Centauri traveling at 30,000 kilometers per second. It crosses the entire star system in hours. Unless the mission includes deceleration, which requires spending the same velocity change in reverse, the spacecraft is a bullet passing through a target, gathering a few hours of data before the destination shrinks into the cosmic distance. We will examine the crippling mathematics of deceleration shortly. Second, we assumed a perfect fusion engine operating at theoretical maximum efficiency. No real engine achieves this. Magnetic confinement, thermal losses, incomplete fuel burn, the mass of the reactor vessel, heat radiators, fuel tanks, and power conditioning equipment all add parasitic mass and reduce effective performance. A realistic fusion engine might achieve 50 to 70% of theoretical exhaust velocity, which worsens the mass ratio significantly. Third, 100,000 kilograms is far too light for any crewed interstellar mission. Scaling to a more realistic payload of 1 million kilograms pushes the total departure mass to 20 million kilograms just for one-way acceleration. Scale to 10 million kilograms, Still modest for a multi-decade crewed vessel, and the departure mass reaches 200 million kilograms. These are enormous numbers, but the exponential nature of the rocket equation ensures they could be far worse at higher speeds. Fourth, and most insidiously, the mass of the fuel itself must be accelerated by other fuel. Every kilogram of fuel added to the spacecraft's tanks increases the total mass that must be pushed to cruising speed. This additional mass requires its own share of fuel, which adds more mass, which requires still more fuel. The rocket equation captures this spiral mathematically through the exponential function, but it helps to feel it intuitively. Imagine filling a truck with gasoline for a long drive, but the gasoline itself weighs so much that you need a bigger truck, which burns more gasoline, which requires an even bigger truck. The spiral compounds until the vehicle is almost entirely fuel, with the useful payload reduced to a tiny fraction of the total mass. Let us walk through this spiral with a concrete example to make the compounding visceral rather than abstract. Start with our 100,000 kilogram spacecraft. We want to accelerate it to 10% light speed using fusion propulsion with an exhaust velocity of 10,000 kilometers per second. The rocket equation tells us the mass ratio is approximately 20. So the total departure mass is 2 million kilograms, 100,000 kilograms of spacecraft, and 1,900,000 kilograms of fusion fuel. Now suppose the mission designers realize they need more radiation shielding. Interstellar hydrogen, even at the extremely low density of roughly 1 atom per cubic centimeter, becomes a serious radiation hazard at 10% light speed. Each hydrogen atom strikes the hull with the kinetic energy of a cosmic ray, so the designers add 10,000 kilograms of shielding, a 10% increase in payload mass. At a mass ratio of 20, this seems manageable. The fuel increases by about 10%, roughly 190,000 additional kilograms. But remember that a mass ratio of 20 applies only to one-way acceleration. The moment you add deceleration, the mass ratio jumps to 403. Now that same 10,000 kilograms of extra shielding does not add 190,000 kilograms of fuel, it adds 10,000 times 402 over 4 million kilograms of additional fuel. A 10,000 kilogram design change has ballooned into a 4 million kilogram fuel penalty. At mass ratio, 403, every kilogram of payload costs over 400 kilograms of fuel. This is why interstellar spacecraft design is not like building an aircraft or even a space station, where adding weight is expensive but proportional. In the regime of high mass ratios, adding weight is catastrophic. A small design change at the payload level cascades through the exponential and emerges at the departure mass level amplified by a factor of hundreds. Mission designers cannot afford to be even slightly wrong about the spacecraft mass, because every error is multiplied hundreds of times over in fuel. This cascading sensitivity also explains why crewed missions are so much harder than robotic probes. A robotic probe can be built to minimal mass, a few hundred kilograms, perhaps a few thousand. The fuel penalty, while enormous in absolute terms, remains within the range of ambitious engineering. A crewed vessel, with all its life support, structural and human needs mass, pushes the payload into a regime where the exponential multiplier becomes overwhelming. The difference between a 100 kilogram probe and a 1 million kilogram crewed ship is not a factor of 10,000 in departure mass. It is a factor of 10,000 multiplied through the exponential, yielding departure masses that differ by staggering amounts. For fusion propulsion at 10% light speed, the payload fraction is about 5%. 95% of the total spacecraft mass is fuel. This is comparable to the payload fraction of modern orbital rockets. The Saturn V's payload was about 1.5% of its launch mass, but the total masses involved are orders of magnitude larger. This is the price of velocity under the constraints of the rocket equation. The energy cost of reaching interstellar speeds is enormous in absolute terms, but the exponential mass penalty imposed by carrying your own fuel transforms enormous into overwhelming. The rocket equation does not forgive. It does not round down. It amplifies every design decision, every safety margin, every contingency into a fuel requirement that can dwarf the payload by factors of hundreds or thousands. And everything we have discussed so far applies to one-way acceleration. No slowing down at the destination, no entering orbit around another star, just a high-speed flyby lasting hours. Making the mission actually useful, making it capable of stopping, studying, perhaps even establishing a presence, requires deceleration. And deceleration, as we are about to see, does not merely double the problem, it squares it. Everything discussed so far relied on classical physics. Kinetic energy equals 1/2 times mass times velocity squared. The rocket equation relates velocity change to exhaust speed and mass ratio through a logarithmic function. These approximations work well at ordinary speeds, and they remain reasonable even at a few percent of light speed. But as a spacecraft pushes toward higher fractions of light speed, classical physics quietly breaks down. The true physics, Einstein's special relativity, confirmed by over a century of experimental evidence, takes over, and the energy problem transforms from severe to catastrophic. In classical physics, there is no theoretical speed limit. You can always add more energy and go faster. The energy cost rises with the square of velocity, but the curve, while steep, never becomes vertical. In principle, given sufficient energy, you could reach any speed you desired. This comfortable picture suggests that interstellar travel is merely a question of scale. Generate enough energy and any velocity is attainable. Relativity destroys this comfort completely. As an object with mass approaches the speed of light, the energy required to accelerate it further does not merely continue rising on the familiar quadratic curve. It departs from the classical prediction, curving upward with increasing steepness, and approaches a vertical asymptote at the speed of light. Light speed is not merely a very high velocity that happens to be hard to reach. It is a fundamental boundary built into the geometry of space-time, a boundary that no massive object can reach no matter how much energy is applied. The energy cost of the final few percent of light speed does not merely increase, it approaches infinity. The mathematical core of this effect is the Lorentz factor, usually represented by the Greek letter gamma. Gamma equals 1 divided by the square root of 1 minus the velocity squared divided by the speed of light squared. At low velocities, the ratio of velocity squared to light speed squared is vanishingly small. Gamma is very close to 1, and relativistic effects are negligible. As velocity approaches light speed, the denominator approaches 0, gamma climbs without bound, and the relationship between energy and velocity becomes fundamentally different from the classical prediction. The relativistic kinetic energy of an object is not calculated by the familiar 1/2 mv² formula. Instead, it equals gamma minus 1 multiplied by the rest mass of the object multiplied by the speed of light squared. At low speeds, this expression simplifies to the classical formula. At high speeds, it grows far faster. The physical intuition behind this divergence is profound. In relativity, as an object accelerates, it behaves as though its effective mass increases. The faster it moves, the harder it becomes to accelerate further. At 90% light speed, pushing the spacecraft feels to the engine like pushing an object more than twice as heavy as it was at rest. At 99%, the effective resistance has grown sevenfold. At 99.9%, the object resists acceleration as though it were more than 22 times heavier than its rest mass. The engine must push harder and harder for each additional increment of speed, and the energy invested in each push grows without bound as the speed approaches the universal limit. This is not a metaphor, it is a measurable physical effect. Electrons in particle accelerators demonstrate this behavior with perfect precision. A particle that weighs a fixed amount at rest requires exponentially more energy to accelerate as it approaches light speed. The Large Hadron Collider spends more energy pushing its protons through the final fraction of a percent toward light speed than was needed for all the preceding acceleration combined. The collider is, in a very real sense, a laboratory demonstration of the interstellar energy wall applied to subatomic particles. Let us trace the numbers through the velocity range that matters for interstellar travel. At 10% light speed, gamma equals approximately 1.005. The relativistic kinetic energy is less than 1% higher than the classical calculation would predict. The energy numbers we calculated earlier remain valid. The energy wall at 10% light speed is real and severe, but it is a classical wall, not yet deformed by relativistic effects. At 20% light speed, gamma is approximately 1.021. The correction is about 2%, still minor. At 30% light speed, gamma reaches approximately 1.048, about a 5% correction. Noticeable to a careful physicist, but not yet dominant. At 50% light speed, gamma climbs to approximately 1.155. The relativistic kinetic energy is now roughly 15.5% higher than the classical prediction. This is where the two calculations begin to visibly diverge. A spacecraft designer who relied on classical energy estimates would underestimate the fuel requirement by 15%, a significant error when mass ratios are already demanding. At 70% light speed, gamma is approximately 1.4. The kinetic energy is 40% higher than the classical formula would give. The relativistic tax has become a major budgetary item. At 80% light speed, gamma reaches approximately 1.67. The correction exceeds 67%. The classical formula is now badly wrong. At 90% light speed, gamma jumps to approximately 2.29. Here the numbers take on a new character. Consider what gamma -1 means in absolute terms. The rest mass energy of our 100,000 kilogram spacecraft calculated via Einstein's E equals mc squared is approximately 9 times 10 to the 21st joules. This is the total energy that would be released if every atom in the spacecraft were annihilated with an equal mass of antimatter, converting all matter entirely into radiation. At 90% light speed, the relativistic kinetic energy is gamma -1, about 1.29 times this rest mass energy. That yields approximately 1.16 times 10 to the 22nd joules. Pause on that number. The kinetic energy of a 100,000 kilogram spacecraft at 90% light speed exceeds the spacecraft's own rest mass energy. You must invest more energy in the spacecraft's motion than would be released by the total annihilation of the spacecraft's mass. The spacecraft must absorb more energy than it contains. The energy of motion surpasses the energy of existence. This is the relativistic wall making itself unmistakable, and it gets dramatically steeper. At 95% light speed, gamma reaches approximately 3.2. The kinetic energy climbs to about 2.2 times the rest mass energy. You now need the energy equivalent of annihilating more than 2 full copies of the spacecraft. At 99% light speed, gamma rises to roughly 7.1. The kinetic energy exceeds 6 times the rest mass energy. 6 spacecraft masses converted entirely to pure energy, all invested in the velocity of a single object. At 99.9% light speed, gamma soars to approximately 22.4. The kinetic energy exceeds 21 times the rest mass energy. At 99.99%, gamma passes 70. The kinetic energy exceeds 69 times the rest mass energy. The pattern is clear and utterly unforgiving. Each small increment of speed toward light speed demands a disproportionately enormous increase in energy. Going from 50 to 90% light speed, a factor of 1.8 in velocity multiplies the energy by a factor of roughly 8. Going from 90 to 99%, an increase of only 9 percentage points, multiplies it by nearly another factor of 5. Going from 99 to 99.9%, less than 1 percentage point of additional speed nearly triples the energy yet again. The curve does not level off. It does not plateau. It rises ever more steeply toward the vertical asymptote at light speed. Every particle accelerator ever built confirms this relationship. At CERN's Large Hadron Collider, Protons are routinely accelerated to 99.9999% of light speed. The energy required to push them that final fraction of a percent closer to light speed exceeds all the energy already invested in reaching their current velocity. The wall is not theoretical, it is observed, measured, and absolute. What makes this particularly cruel for interstellar mission design is the shape of the energy curve in the velocity regime that matters most. Between 10 and 50% of light speed, the relativistic corrections are modest, a few percent to about 15% above the classical prediction. This is the regime where the energy problem is already severe due to the quadratic scaling of kinetic energy, but where the relativistic tax is not yet the dominant factor. A mission designer working in this speed range could be forgiven for thinking that the challenge, while enormous, is fundamentally classical in nature, a problem of generating enough energy through sufficiently advanced technology. But push above 50% of light speed, and the character of the problem changes. The relativistic correction grows from a modest surcharge into the dominant cost factor. By 90% light speed, the true kinetic energy is more than double what the classical formula would predict. By 99%, it is more than triple the classical value. The curve has steepened into something qualitatively different, not merely expensive, but approaching a regime where each additional kilometre per second of velocity costs more energy than the last several thousand kilometres per second combined. This means there is a zone in the velocity landscape roughly between 30 and 90% of light speed where the travel times are most attractive and the energy costs are most rapidly escalating. A mission at 30% light speed reaches Alpha Centauri in about 14 years. A mission at 90% arrives in under 5 years. These are excellent transit times for a crewed mission. They are also the speeds where the energy curve is steepest and the price per additional increment of velocity is climbing most rapidly. There is no velocity sweet spot where both the travel time is short and the energy cost is manageable. The universe has arranged the physics so that comfortable energy costs correspond to long travel times measured in many decades, while short travel times in the range of years to a couple of decades correspond to energy costs that scale explosively towards civilization-breaking levels. You cannot have both. Every attempt to shorten the journey drives the mission deeper into the steepest section of the energy curve. This trade-off is not a design choice. It is not something that can be engineered around with a sufficiently clever mission profile. It is a direct consequence of how kinetic energy and relativistic mass energy relate to velocity. The universe offers a menu with 2 columns, affordable energy and long travel time, or short travel time and ruinous energy. There is no hidden third column. For interstellar travel, the relativistic wall means that the speeds most appealing from a travel time perspective, speeds where the journey to Alpha Centauri takes years rather than decades, are precisely the speeds where energy costs become most extreme. 90% light speed delivers a crew in about 4.7 years, a wonderful transit time. But the energy cost for even our tiny 100,000 kilogram spacecraft exceeds 20 times the annual energy consumption of all human civilization. 20 full years of total global energy output for one small spacecraft. Acceleration only. This brings us to the second devastating blow, deceleration. Everything discussed so far, every energy calculation, every mass ratio, every comparison to civilization scale output, has assumed the spacecraft simply accelerates to cruising speed and coasts. It arrives at the destination star system at whatever fraction of light speed it was traveling and keeps going. It rockets through the target system and continues into the void beyond. Let us feel what a flyby at 10% light speed actually means. Your spacecraft has traveled for 43 years. The crew has aged from youth to retirement aboard this vessel. They have maintained life support systems, repaired equipment, raised children perhaps, endured the psychological weight of decades in a metal tube, crossing the emptiness between stars. Alpha Centauri grows from a point of light to a visible disk over the final weeks of approach. Then arrival happens. At 30,000 kilometers per second, the spacecraft crosses the habitable zone of Proxima Centauri, the region where the planet Proxima Centauri b orbits in a matter of minutes. Not hours, not days, minutes. The entire star system, from its innermost orbits to its outermost cometary halo, passes in a matter of hours. Any photographs must be taken in the fleeting window of closest approach. Any spectral readings, any atmospheric analysis, any measurements of surface conditions on the planet you spent 43 years travelling to reach are compressed into a window shorter than a lunch break. And then it is over. Proxima Centauri shrinks behind the spacecraft, dwindling back into a point of light indistinguishable from the billions of others. The crew watches their destination recede at 30,000 kilometers per second, growing dimmer with each passing hour. They have no way to stop, no way to turn around, no way to go back. Their spacecraft will continue into the interstellar void, eventually reaching the next star system in another several decades where, if they are still alive, the same fleeting flyby will repeat. 43 years of travel for a few minutes of proximity. This is what a mission without deceleration looks like. It is not a mission. It is a very expensive wave as you pass by. For any mission of genuine scientific or existential value, one that enters orbit around a planet, deploys instruments, lands, probes, studies surfaces, samples atmospheres, or establishes any kind of sustained presence, the spacecraft must decelerate. It must shed its interstellar velocity entirely, arriving at something approaching rest relative to the target star. This requires applying thrust in the opposite direction, spending energy to slow down, and burning fuel to counteract the velocity the mission worked so hard to achieve. In principle, deceleration is symmetric with acceleration. The same velocity change is required. The same amount of energy must be removed from the spacecraft's motion. But in practice, deceleration is vastly more punishing than acceleration because of how it interacts with the rocket equation. There is an additional complication that makes matters worse still at higher speeds. The classical rocket equation, derived by Tsiolkovsky, applies to low velocities where relativistic effects are negligible. But at speeds above roughly 20% of light speed, the relativistic rocket equation must be used instead. The relativistic version accounts for the fact that exhaust ejected from a fast-moving spacecraft does not carry away as much momentum as classical physics would predict. Because the velocities of the spacecraft and its exhaust do not simply add together, they combine, according to Einstein's velocity addition formula. The result is that the mass ratio required for a given velocity change is even larger in the relativistic regime than the classical rocket equation predicts. The classical equation, which already yields crushing numbers, actually underestimates the fuel requirement at high fractions of light speed. The true numbers are worse. When a spacecraft carries fuel for deceleration, that deceleration fuel is dead weight during the entire acceleration phase. Every kilogram of fuel reserved for braking at the destination must be accelerated to cruising speed along with the payload. The engines spend energy pushing mass that will not be useful until the very end of the mission. This dead weight increases the total mass that must be accelerated, which requires more acceleration fuel, which adds more mass, which demands still more fuel. The rocket equation handles this automatically. You calculate the mass ratio for the total velocity change acceleration plus deceleration combined, rather than computing two separate mass ratios and adding them. And because the rocket equation is an exponential function, the combined mass ratio is not the sum or even the product of two separate ratios in any simple sense. It is far, far worse. For fusion propulsion with an exhaust velocity of 10,000 kilometers per second, the mass ratio for acceleration alone to 10% light speed is e to the power of 3 approximately 20. One-way trip, no braking. The mass ratio for accelerating to 10% light speed and then decelerating back to rest, a total velocity change of 60,000 kilometers per second, is e to the power of 6. That is approximately 403. Notice what happened. Doubling the velocity change from 30,000 to 60,000 kilometers per second did not double the mass ratio from 20 to 40. It raised the exponent from 3 to 6, which raised the mass ratio from 20 to 403. This is the nature of exponential functions. Doubling the exponent does not double the result, it squares it. 20 squared is 400. The deceleration penalty is not additive, it is multiplicative in the most devastating sense. For our 100,000 kilogram spacecraft, a mass ratio of 403 means a total departure mass of approximately 40 million kilograms, 40,000 metric tons. The Saturn V, the largest launch vehicle ever flown, could deliver roughly 130 metric tons to low Earth orbit. Assembling the fuel alone for one interstellar mission at 10% light speed with deceleration would require the lift capacity of over 300 Saturn V launches. The International Space Station took over a decade and dozens of launches to assemble 420,000 kilograms in orbit. The fuel for a single interstellar mission would mass roughly 100 times more. Push the speed to 20% light speed with deceleration, and the numbers leave the realm of even ambitious engineering. The total velocity change is 120,000 kilometers per second. The mass ratio is e to the power of 12, approximately 163,000. For every kilogram that arrives and stops, over 163,000 kilograms must depart. A 100,000 kilogram payload requires a departure mass of roughly 16.3 billion kilograms. That is 16 million metric tons. For a single mission, 16 million metric tons is roughly 7 times the mass of the Great Pyramid of Giza, or equivalent to stacking 40 of the largest supertankers ever built. Assembling this mass in orbit, fueling it, and directing it toward another star is not engineering as we currently practice it. It is a feat that would redefine what civilization means. At 50% light speed with deceleration, the mass ratio is e to the power of 30, approximately 10.7 trillion. The departure mass for a 100,000 kilogram payload exceeds 1 billion metric tons. The numbers have become physically meaningless. This mass exceeds that of a small moon. Some might ask whether deceleration can be avoided entirely. Perhaps the spacecraft could aerobrake use atmospheric drag to slow down, the way returning space capsules use Earth's atmosphere. But this requires the destination to have a thick atmosphere, which not all potentially habitable worlds do. More critically, a spacecraft arriving at even 10% of light speed carries kinetic energy so enormous that any attempt to shed it through atmospheric drag would produce temperatures sufficient to vaporize the spacecraft and a substantial portion of the atmosphere it was entering. Aerobraking works at orbital velocities of a few kilometers per second. At tens of thousands of kilometers per second, it is not braking. It is an explosion. Others have suggested gravitational braking swinging around the destination star to shed velocity through gravitational interactions. But gravitational assists can only change a spacecraft's velocity by an amount comparable to the orbital velocity of the body being used for the assist. Even a close flyby of a sun-like star provides a velocity change measured in hundreds of kilometers per second, at most a tiny fraction of the tens of thousands of kilometers per second the spacecraft needs to shed. Gravitational braking is irrelevant at interstellar velocities. The hard truth is that any spacecraft arriving at a distant star system at a significant fraction of light speed must carry the means to decelerate, whether that means carrying fuel, deploying a magnetic sail, or relying on an external energy source that has somehow been pre-positioned at the destination. Every option either adds mass to the departure vehicle, which compounds through the rocket equation, or requires a prior mission to the destination, which faces the same energy wall. This creates what might be called the deceleration paradox of interstellar travel. The most efficient mission profile, accelerate hard, coast at high speed, arrive quickly, is also the most expensive to stop. The cheapest missions to brake from those travelling at very low speeds take so long that crude travel becomes impractical. The physics offers no compromise. Short travel times and affordable deceleration are mutually exclusive. Map the trade-off in your mind. At 5% light speed with deceleration, the travel time is about 85 years too long for a single crew, but conceivable for a generation ship, and the fuel requirement, while enormous, remains physically meaningful. Push to 10% and the journey shrinks to about 43 years, barely within a human lifespan, but the fuel demand has leapt by a factor of 20. Push to 20%, and a wonderfully short 21-year transit comes at the cost of fuel masses that exceed the capacity of any conceivable space-based construction program. The faster you go, the more attractive the travel time, and the more impossible the fuel. The only speed regime where both the travel time and the mass ratio are simultaneously manageable, if we define manageable as a few decades of travel, and a mass ratio below a few hundred, sits in a narrow band around 5 to 10% of light speed. This is the only window the physics allows, and it is razor thin. Below this band, travel times stretch beyond human patience. Above it, fuel requirements exceed human capability. This narrow window is the practical expression of the energy wall. It is not a wall in the sense of an absolute prohibition. It is a wall in the sense of a steeply rising cost that confines realistic interstellar missions to a tiny region of velocity space. You can peer over the wall and imagine faster missions, but the price of climbing higher rises so steeply that each additional percentage point of light speed costs more than all the previous ones combined. To appreciate how narrow this window is, consider the full range of possible speeds. Light speed represents the theoretical maximum. The useful interstellar range spans from about 5% to perhaps 15 or 20% light speed if we allow extremely ambitious mass ratios. That range, expressed as a fraction of the theoretical maximum, is roughly 5 to 20%. The universe offers a usable velocity band that is only about 15 percentage points wide. Below this band, missions take too long for human relevance. Above it, the energy and mass requirements exceed the capacity of any civilization that does not command stellar-scale energy resources. The window exists not because of any particular propulsion technology's limitations, but because of how kinetic energy, the rocket equation, and the deceleration requirement interact across the velocity spectrum. A different propulsion system might shift the window slightly, widen it by a few percentage points, narrow it by a few, but the window's existence is a consequence of physics, not engineering. This is perhaps the most sobering insight of the entire analysis. The dream of interstellar travel, if it is achievable at all with known physics, is confined to a narrow corridor of velocities where the journey takes decades. The fuel requirements are enormous, but not physically impossible, and the technology required fusion at minimum does not yet exist. There is no fast lane. There is no shortcut that reduces travel times to years while keeping costs manageable. The universe simply does not permit it. The combined effect of relativistic energy scaling and the deceleration tax creates a triple barrier of extraordinary severity. Each component alone is daunting. Together, they are almost certainly the most formidable obstacle any civilization faces when it contemplates traveling between stars. The relativistic wall ensures that higher speeds demand not just more energy, but exponentially more energy per increment of velocity. The rocket equation ensures that carrying fuel imposes an exponential mass penalty that grows with every additional kilometer per second of desired velocity change. And the deceleration requirement roughly doubles the velocity change, which in exponential terms does not double but squares the mass ratio. These three effects, quadratic energy scaling that becomes relativistic divergence, exponential fuel requirements, and the deceleration multiplier compound upon each other. They create a landscape where the most attractive missions, the ones with reasonable travel times, sit behind the steepest part of the energy wall. Modest missions at low speeds are energetically feasible but take decades or centuries. Fast missions that could transport crews within a human lifetime require energy and mass budgets that dwarf anything our civilization has ever attempted. The wall is real, and the final question remains: can any propulsion concept, however advanced, find a path through it, or does every technology, no matter how exotic, eventually collide with the same limit? That question demands testing the most promising candidates against the physics and observing what survives. The previous 3 parts established the energy wall through fundamental physics alone. Kinetic energy's quadratic rise with velocity, sharpened to a divergence by special relativity. The rocket equation's exponential relationship between velocity change and fuel mass. The deceleration tax that compounds the exponential into something approaching physical absurdity. Together, these constraints create a barrier whose severity is determined not by the state of human technology, but by the structure of the laws of motion. The barrier would exist in any universe governed by conservation of energy and special relativity, regardless of who or what attempted to cross it. The question now is whether any propulsion concept, no matter how advanced, no matter how far beyond current engineering, can circumvent the wall or reduce it to something a technological civilization could reasonably pay. The answer, grounded in the physics we know, is no. But establishing this requires testing the most promising candidates one by one and observing where each of them breaks against the same fundamental limits. Begin with fusion propulsion, the most frequently cited candidate for serious interstellar missions. Fusion is the process that powers every star in the visible universe. It converts light atomic nuclei, primarily isotopes of hydrogen, into heavier nuclei, releasing energy in the process. The energy yield per kilogram of fuel exceeds chemical combustion by a factor of roughly 10 million, where burning hydrogen and oxygen releases about 13 million joules per kilogram. Fusing deuterium and helium-3 releases approximately 350 trillion joules per kilogram. A fusion engine could theoretically achieve exhaust velocities of several thousand to perhaps 15,000 kilometers per second, depending on the nuclear reaction used and the efficiency of the magnetic nozzle directing the exhaust. The physics is sound. The engineering remains unfinished. Sustained, net positive fusion power has been a goal of physics research since the 1950s. After more than 70 years of effort and cumulative global investment exceeding $60 billion, no fusion reactor has yet produced more energy than it consumes for any sustained period. The ITER project in southern France, the largest fusion experiment ever built, aims to demonstrate net energy gain in controlled fusion, but significant milestones remain years away. Even if ITER succeeds in all its objectives, the path from a massive stationary ground-based reactor to a compact, lightweight, space-rated engine that operates continuously for decades in deep space spans engineering challenges that no current program addresses. Grant fusion propulsion anyway. Assume a theoretically perfect engine. No structural mass penalty, no thermal losses, maximum exhaust velocity of 10,000 kilometers per second. As we have already seen, the mass ratios for interstellar speeds with deceleration range from hundreds to 1 at the lowest useful velocities to hundreds of thousands to 1, where travel times become truly attractive. The fuel masses climb from tens of millions to billions of kilograms even for a modest payload. Fusion is vastly superior to anything humans have built. It would transform interstellar travel from a mathematical impossibility into a merely colossal engineering challenge at the lowest useful speeds. But the exponential rocket equation ensures that fusion cannot unlock higher velocities. Every attempt to push faster slams into the same exponential wall that defeated chemical rockets merely shifted to a higher velocity regime. The wall moves, but it does not fall. Some designs attempt to escape the rocket equation entirely by collecting fuel from the environment. The Bussard ramjet, proposed in 1960 by the physicist Robert Bussard, imagines a spacecraft that scoops hydrogen from the thin gas between the stars and feeds it into an onboard fusion reactor. If the interstellar medium provides the fuel, the spacecraft carries none. The rocket equation becomes irrelevant. Continuous acceleration becomes possible for the entire journey. The concept is beautiful. The physics is unkind. The interstellar medium in our galactic neighborhood contains roughly 1 hydrogen atom per cubic centimeter. This is an extraordinarily low density, a vacuum far more perfect than any achievable in a terrestrial laboratory. To collect enough hydrogen to fuel a fusion engine producing meaningful thrust, the collection scoop, whether a physical structure or an electromagnetic funnel, would need to sweep a cross-sectional area measured in hundreds or thousands of kilometers. But collecting interstellar hydrogen at high velocities is not like gently sweeping up dust with a broom. At 10% of light speed, each incoming hydrogen atom carries kinetic energy equivalent to being struck by a small bullet. The collective impact of trillions of hydrogen atoms per second striking the spacecraft and its scoop creates drag and aerodynamic resistance force that opposes the spacecraft's motion. Detailed analyses published in the late 1970s and early 1980s demonstrated that at velocities above a few percent of light speed, the drag from the incoming interstellar medium exceeds the thrust that can be generated by fusing the collected hydrogen. The ramjet produces net deceleration rather than acceleration. It slows down instead of speeding up. The faster it goes, the worse the problem becomes. Additionally, fusing ordinary hydrogen proton-proton fusion, the reaction that powers the sun, is extraordinarily difficult to initiate and sustain in a compact reactor. The sun manages it only because of its immense size and the crushing pressure at its core. Proton-proton fusion has the lowest reaction rate of any fusion process. A practical fusion engine would prefer deuterium-tritium or deuterium-helium-3 reactions, but these isotopes are vanishingly rare in the interstellar medium. The fuel available for free between the stars is not the fuel you would choose to burn. Modified versions of the ramjet concept exist. Some propose using the scoop only as a source of reaction mass, collecting interstellar hydrogen and expelling it at high velocity using onboard energy from a carried power source such as antimatter or beamed energy. This avoids the drag problem at the cost of reintroducing the need to carry energy, which brings mass penalties back into play. Others propose a RAM-augmented interstellar rocket that carries its own fuel for the initial acceleration phase and then transitions to ramjet mode once the velocity is high enough for efficient collection. These hybrid concepts are clever, but they do not eliminate the energy wall. They redistribute its costs without reducing the total. Now consider the theoretical ceiling of propulsion efficiency, antimatter. When a particle of matter encounters its corresponding antiparticle, they annihilate completely, converting 100% of their combined rest mass into energy via Einstein's mass-energy equivalence. No physical process in the known universe extracts more energy per kilogram of fuel. A perfect antimatter rocket, in which matter and antimatter annihilate and the resulting energy is perfectly directed as exhaust, would achieve an effective exhaust velocity approaching the speed of light itself. At such extreme exhaust velocities, the rocket equation becomes remarkably gentle. To reach 10% light speed and decelerate to rest, a total velocity change of 20% light speed, the required mass ratio is e to the power of approximately 0.2, which equals about 1.22. For every kilogram of payload, you need only about 0.22 kilograms of fuel, half matter, half antimatter. For a 100,000 kilogram spacecraft, the total fuel mass is roughly 22,000 kilograms, 11,000 kilograms of antimatter, plus 11,000 kilograms of ordinary matter. At 50% light speed with deceleration, the antimatter mass ratio is approximately 3:1. At 90% light speed with deceleration, the relativistic photon rocket equation pushes the mass ratio to approximately 19:1, far higher than a naive classical calculation would suggest, because relativistic velocity addition makes the exhaust less effective at these speeds. Still, these are mass ratios that engineering could conceivably handle. Antimatter propulsion, alone among all propulsion concepts, yields manageable fuel requirements across the range of useful interstellar velocities. This is why antimatter is sometimes called the ultimate rocket fuel. It, and it alone, tames the rocket equation at interstellar speeds. But the energy wall does not disappear. It shifts from the spacecraft to the antimatter factory, and the magnitude of the shift is devastating. Antimatter does not exist naturally in useful quantities anywhere in the observable universe. The cosmos is overwhelmingly composed of ordinary matter. The reason for this asymmetry, why the Big Bang produced slightly more matter than antimatter, remains one of the deepest unsolved problems in particle physics. But the practical consequence for propulsion is simple and severe. Every nanogram of antimatter must be manufactured. Manufacturing antimatter requires particle accelerators. High-energy collisions between protons or electrons occasionally produce particle-antiparticle pairs. The antiparticles must then be captured, cooled, and stored before they contact any normal matter and annihilate. The process is spectacularly inefficient. Current particle accelerators convert roughly 1 part in 10 billion of their input energy into usable antimatter. The rest is dissipated as heat, unwanted radiation, and particle species that cannot be used. The total amount of antimatter ever produced by all human particle physics laboratories combined, over decades of operation, at facilities including CERN, Fermilab, and Brookhaven, is estimated at approximately 20 nanograms, 20 billionths of a gram. The energy content of this antimatter, if fully annihilated with an equal mass of ordinary matter, would be sufficient to heat a cup of coffee, perhaps light a small light bulb for a few seconds. The total cost of producing it, spread across the operating budgets of the world's accelerator facilities, exceeds many billions of dollars. Producing antimatter in quantities relevant to propulsion kilograms, tens of kilograms, let alone the 11,000 kilograms, our modest 10% lightspeed mission requires would demand energy inputs so vast they strain comprehension. Even if antimatter production efficiency improved by a factor of 1 million over current capabilities, a technological leap with no clear path, manufacturing 11,000 kilograms would require approximately 2 times 10 to the 24th joules of input energy. That equals roughly 3,500 years of total human energy production at current rates. To put this in perspective, 3,500 years ago, the ancient Egyptians were building the temples at Luxor. Every joule of energy produced by every human civilization from that day to this, every campfire, every steam engine, every nuclear reactor, every solar panel would not suffice to manufacture the antimatter for a single interstellar mission, and this assumes a million-fold improvement in production efficiency that no current technology trajectory promises. Even if a future civilization could produce antimatter more efficiently, perhaps by using dedicated particle factories powered by orbital solar collectors, the total energy investment remains fixed by the energy content of the brews. Antimatter itself, plus the unavoidable inefficiency of the production process. You cannot create energy from nothing. You can only convert it from one form to another. The energy that will eventually propel the spacecraft must first be gathered, concentrated, and invested in antimatter production. The total bill does not shrink. It merely gets paid at a different counter. The energy wall has not been breached. It has merely changed address. Instead of carrying impossible quantities of conventional fuel, you now face the impossible energy cost of manufacturing the most efficient fuel that physics permits. The universe allows you to choose your method of payment, carry fuel on the spacecraft, manufacture exotic fuel on the ground, beam energy from a remote source, but it does not reduce the total. The energy required to move mass at interstellar speeds is determined by the laws of motion, and no chemistry, no nuclear physics, and no engineering can change those laws. Antimatter storage adds another layer of difficulty. Antiprotons annihilate instantly on contact with any ordinary matter, releasing gamma radiation with energies of hundreds of millions of electron volts per annihilation event. Storing macroscopic quantities of antimatter requires magnetic or electrostatic traps that maintain containment without any physical contact between the antimatter and its container walls. These traps must operate flawlessly for the duration of a multi-decade interstellar mission, through the mechanical stresses of acceleration and deceleration, through the radiation environment of deep space, and through any equipment failures or degradation that occurs over decades without resupply. No such storage system exists. No prototype has been demonstrated. The engineering challenges are formidable even in principle. And the consequences of failure: instantaneous annihilation of the fuel supply, with catastrophic energy release, make antimatter storage one of the most unforgiving engineering problems ever contemplated. Now consider the most creative approach to the propulsion problem: eliminating onboard fuel entirely by using external energy. Laser sail concepts represent the purest expression of this idea. The Breakthrough Starshot Initiative, announced in 2016 with funding from technology investor Yuri Milner and scientific guidance from the late Stephen Hawking, proposes accelerating gram-scale probes to 20% the speed of light using a powerful ground-based or space-based laser array. The probes carry no fuel and no engine. They deploy lightweight reflective sails a few meters across. A coherent laser beam, fired from the vicinity of Earth, pushes against the reflective surface of the sail, transferring momentum to the probe without requiring any onboard mass expenditure. The probe accelerates for as long as the laser illuminates its sail, roughly 10 minutes for the baseline concept, and then coasts to the destination at 20% light speed. For gram-scale probes, this concept elegantly sidesteps the rocket equation. There is no fuel to carry, no exponential mass penalty, no tyranny of logarithms. The energy comes from an external source that stays behind. A 1-gram probe with a sail of perhaps 4 meters diameter could in principle reach 20% light speed under illumination from a laser array, producing approximately 100 gigawatts of optical power. At that speed, it would reach Alpha Centauri in roughly 20 years and transmit data back to Earth using a small onboard laser or radio system. 100 gigawatts for 10 minutes is about 60 trillion joules, a large but not inconceivable energy investment for a major international project. For comparison, the total electrical generation capacity of the United States is roughly 1,100 gigawatts. The Starshot laser array would need roughly 10% of American electrical capacity directed into a single coherent beam for 10 minutes. Enormous, but physically possible. For gram-scale probes, laser sails may actually work. Breakthrough Starshot is arguably the most physically grounded interstellar concept ever seriously proposed, precisely because it accepts the energy wall rather than trying to defeat it. It minimizes mass to the absolute limit a gram, perhaps a few grams to keep the energy affordable. It uses external power to avoid the rocket equation, and it accepts a flyby mission profile to avoid the deceleration problem entirely. These are profound compromises. The probe carries no meaningful payload, no scientific instruments beyond perhaps a camera and a communication chip, cannot slow down, and flies past the target star system in a matter of hours. But the compromises work because they respect the physics. The problem arises immediately when you try to scale laser sails beyond gram-scale probes. Energy delivery scales linearly with mass. Double the mass, double the required laser power. A 1 kilogram probe demands 100 terawatts. A 1,000 kilogram probe demands 100 petawatts. A 100,000 kilogram crewed spacecraft, still far too small for any real interstellar mission, would require approximately 10 exawatts of coherent laser power, sustained for an extended acceleration period. 10 exawatts is approximately 500,000 times the total power consumption of human civilization. Building a laser array of this power would require capturing and converting a significant fraction of the sunlight falling on an entire hemisphere of a planet, or deploying solar collectors across millions of square kilometers of space, then focusing all of that energy into a coherent beam aimed at a sail that might be light hours away with pointing accuracy measured in billionths of a degree. And even this planetary-scale laser array does not solve deceleration. The probe arrives at Alpha Centauri at 20% light speed and flies past. For a crewed mission that must stop, you need either onboard fuel, reintroducing the rocket equation in all its tyranny, or a second laser array at the destination to push against a forward-facing sail and slow the craft down. Building a laser array at Alpha Centauri requires having already sent a mission there to construct it, creating a temporal chicken-and-egg problem with no clean resolution. Magnetic sail deceleration has been proposed, A large superconducting loop generates a magnetic field that deflects charged particles in the interstellar medium, creating a braking force. Calculations show this might work at modest speeds, a few percent of light speed, but the braking force drops as velocity decreases, potentially leaving the spacecraft still traveling too fast to enter orbit. At higher speeds, the forces on the magnetic structure become extreme, and the sail must be correspondingly enormous and robust. Using the destination star's radiation pressure for deceleration has also been studied. As the spacecraft approaches a star, photons from that star push against a reflective sail, gradually slowing the craft. But the photon pressure from a star at interstellar distances is minuscule. The deceleration would be extremely gradual, requiring sails of extraordinary size and approach geometries that might not align with the desired orbit. Every propulsion concept tested against the wall breaks in the same place. The energy required to move mass at interstellar speeds is fixed by physics. Different systems change where the energy comes from, how it is stored, and how it is applied. Chemical rockets carry chemical energy. Fusion rockets carry nuclear binding energy. Antimatter rockets carry mass energy equivalence at its maximum. Laser sails receive energy from an external electromagnetic source. Each concept has its own elegance, its own engineering challenges, its own failure modes. But not one of them, not a single concept that has ever been studied seriously, reduces the fundamental energy cost of moving a given mass to a given speed. That cost is established by the relationship between kinetic energy and velocity, and by the geometry of space-time that governs how energy, mass, and velocity relate to each other. This is the core distinction between a technological barrier and a structural barrier. A technological barrier falls when the right invention arrives. The sound barrier was technological jet engines, and swept wings overcame it. Reaching orbit was technological staged, liquid fuel rockets overcame it. Reaching the moon was technological Saturn V overcame it. In each case, a cleverer deployment of known physics defeated the barrier, and what was once impossible became routine within a generation. The interstellar energy wall is structural. It is not a consequence of chemical rockets being too weak, or fusion being unfinished, or antimatter being rare. It is a consequence of the relationship between mass, velocity, and energy, a relationship that is among the most thoroughly confirmed in all of physics, validated by every experiment conducted from Galileo's inclined planes to the Large Hadron Collider's relativistic protons. No propulsion system can alter this relationship because it is not a product of propulsion. It is a product of the universe's architecture. The wall is universal in its application. The cost of an interstellar mission is set by three non-negotiable demands: the kinetic energy of the payload, which scales with the square of velocity and diverges relativistically; the fuel penalty of the rocket equation, which compounds exponentially with every additional kilometer per second of desired speed; and the deceleration tax, which roughly doubles the required velocity change, and therefore squares the mass ratio. These three demands create a cost structure that steepens with every increase in speed, every additional kilogram of payload, and every requirement that the spacecraft actually stop at its destination. Some have noted that human energy production has grown roughly exponentially over the past 2 centuries. If this trend continues for centuries more, the energy available to future civilizations may eventually reach levels sufficient for interstellar missions. A civilization that captures a meaningful fraction of its parent star's luminosity, a Kardashev Type II civilization. In the classification proposed by the Soviet astronomer Nikolai Kardashev in 1964, would command roughly 3.8 times 10 to the 26th watts. This is sufficient to power antimatter factories, laser arrays, or fusion fuel production at scales relevant to interstellar travel. But this observation does not diminish the wall, it confirms it. The energy barrier is so severe that it requires a civilization to restructure its entire relationship with its parent star, to transition from harvesting a planet's resources to harvesting a star's output before interstellar missions become energetically realistic. The barrier is not about building a better engine or discovering a new fuel. It is about becoming a fundamentally different kind of civilization, one that operates at stellar scales rather than planetary ones. Such a transformation might take centuries or millennia. It might be achievable, or it might not, but the wall will wait, unchanged and unchangeable, because it is not a human limitation, it is a cosmic constant. Some might ask whether unknown physics wormholes, warp drives, or other speculative mechanisms could someday bypass the wall entirely. These concepts exist in theoretical physics, but none has been shown to be physically realizable. Wormholes require exotic matter with negative energy density, a substance that has never been observed and may not exist. Warp drives, as formulated by the physicist Miguel Alcubierre in 1994, require negative energy in quantities that may exceed the mass energy of the observable universe. These ideas are fascinating as mathematics. They are not propulsion systems. Invoking them as solutions to the energy wall is equivalent to solving a financial crisis by assuming the discovery of a new physical law that permits unlimited money creation. It might happen. It is not a plan. The terrifying conclusion of this analysis is not that the stars are far away. Distance is a familiar adversary. Humans have crossed oceans, continents, and the vacuum between worlds. Each time, we built the technology to match the challenge and succeeded. Distance, in itself, is merely a matter of patience and propulsion. The terrifying conclusion is that the universe has embedded a price in the structure of space-time, a price that scales with breathtaking severity as you increase the speed and mass of anything attempting to travel between stars. That price is energy, and the bill is written in quantities that dwarf the total output of planetary civilizations by factors measured in years, decades, or centuries of total production. The energy wall does not forbid interstellar travel in the way that perpetual motion is forbidden. It does not violate any conservation law to imagine a spacecraft reaching another star and stopping there. The physics permits it. But the physics also ensures that the cost of passage is set not by human cleverness, but by the mass of the spacecraft, the velocity of the journey, and the immutable laws that govern motion in our universe. Those laws do not negotiate. They do not bend to ambition. They do not soften with the passage of time. They apply with identical rigor to a rocket launched from Cape Canaveral today and to a starship launched by a civilization 1 billion years older than ours, orbiting a star on the other side of the galaxy. The stars are not merely distant, they are expensive, and the currency is energy on a scale that transforms interstellar travel from an engineering project into a civilizational test, a test of whether a species can marshal the output of its star to pay the price. The universe demands. That is the true barrier, not the emptiness between the stars, but the energy the universe charges for crossing it. The wall is not built of matter or radiation. It is built of mathematics, the deep, unchangeable mathematics of mass, velocity, and energy, and it will stand as long as the laws of physics hold.